All right, well, thank you very much for the introduction, Christian. So if John went full magic school bus all the way into the details, we're going to take a step back here. We're going to be viewing performance through the lens of sparse linear algebra because Trilinos, right? That's what I work on. Trilinos users group tomorrow. There's a commercial. I'll be doing a bit more detail about what we're doing in performance monitoring there as part of our regular system, but that's not what I'm going to be talking about here. We're going to look in a bit more detail about things. So this is a commercial for tomorrow. We test in a lot of different systems. This is performance tests that we run nightly, right? This is not CI. This is looking at performance and trying to figure out what's happened nightly. And this is a DOE-centric view of the universe, for sure. We've got our mini crossroads machines. There's Tachi and Rocinante. You see Frontier. You see your mini El Caps, RZ Adams, and Eldorado. And then you've got a bunch of other systems across the space, including actual honest-to-goodness Aurora. So we're looking at those. And one of the cool things about gathering performance data on different machines is we can then say, well, let's compare across them and see what happens. And so what we're going to do today is not necessarily look at the full set of performance things across machines, but we're going to look at sort of CPU and GPU architectures and play a little guessing game as to what we can expect. So I'll start by asserting, and then we'll look and see whether or not I'm right, the memory bandwidth is what matters for sparse linear algebra. So roofline plots, if you've never seen one before, welcome to HPSF. But horizontal axis, right, that's operational intensity, flops per byte, vertical axis is performance in gigaflops. This is like the only time I will ever believe gigaflops is a number as part of a roofline plot. And that's Perlmutter in blue, which is at A100, NVIDIA A100. And then you've got Amber, which is a Sapphire Rapids with DDR5. So that's your stock CTS2 machine. And you see two regimes. You've got a diagonal line, that is your memory bandwidth down regime. And then you've got a horizontal line, which is your computational, sort of compute limited regime. For things that look like sparse linear algebra, you're way on the left-hand side of the plot. So vector addition and double precision is there. Even if you said, well, what if I did float? You'd shift a factor of 2 to the right. FP16 is 2 factors of 2. Like, you're nowhere near a compute-dominated regime. This is different from stuff like lamps, where you are. But sparse linear algebra, you're there, and so memory bandwidth is what matters. I'll assert that. We'll kind of revisit that in a bit. So what am I looking at? So these are part of our Trilinos performance test suite, and I'm going to do two kinds of problems here. I'm going to do strong scaling and weak scaling. So our strong scaling problems, we're going to start with our unpreconditioned CG. 8 million degrees of freedom, so that's more than enough to keep a GPU busy, and we're going to just throw more compute at it. So all the tests I'm going to show you are going to run on a single node, so we don't have to worry about network issues. Also, I can get a single node every night. I can't get like 100 on these computers. And then we're going to do finite element assembly. Again, it's a strong scaling, and that's 8,000 squared elements, right? So it's in 2D. We're going to look at two weak scaling tests that are supposed to be more application-like, and these are based on our algebraic multigrid solver, MULU. There's going to be a setup phase that's going to be dominated by things like sparse matrix multiplication. And there's going to be a solve phase, which should look like SPMV. And that's going to be weak scaled. I'm going to make the problem bigger as I throw more ranks at it. So those are my test problems I'm going to use. And we're going to take a look and zoom in at a couple machines. So we're going to start on the CPU side. So here are the machines I'm playing with. So I'm going to start with an older CTS1 machine that's Broadwell. It's Eclipse. And so that's 36 cores across 2 sockets. It uses DDR4. And it's got a notional 150 gigabytes a second worth of memory bandwidth. And if you run stream, you can actually get pretty close to that. The second one is Amber, which you saw earlier. That's Sapphire Rapids with DDR5. It's got like 4 times the memory bandwidth, although you can't quite get as much out of that in practice when you run stream. But yay, right? Like, I did nothing, and my code, if memory bandwidth is to be believed, got 3 to 4 times faster. Fantastic. I'm going to skip Blake for a second. I'm going to go down to Tachi. Tachi is mini crossroads. That's Sapphire Rapids, just like Amber, but now it uses HBM2. And so notionally, you've got a whole lot of memory bandwidth on the tin. The number I have that I got with stream is lower. Some other folks have gotten a little better than that. And I'll get back to that in a second. Then we've got Blake, which is Granite Rapids, which I managed to get a Granite Rapids that isn't NDA covered, so I can talk about it, which is awesome. So that's 256 cores on a single node, which is kind of crazy, and it uses these sort of new MRDIMM technology, notionally about 1.7 terabytes a second memory bandwidth, and you can actually get that out of stream. And then finally, we'll look at the Grace superchips. That's a pair of Graces, 72 cores a pop, LPDDR5, notionally a terabyte a second, most of which is achievable. Everything I'm going to show you here is going to use the Intel 2025, where I can get it to work. It did not work on Eclipse for whatever reason, so I'm stuck with 2024, and the Grace 2025. So since I'm using stock compilers, you might ask questions like, well, you know, are the MPI bindings right? The answer is probably not. But once you get enough cores firing, that probably matters less. And again, to be frank, MPI bindings at sub-full core counts are always an iffy thing anyway. So I will call out two things here, specifically Crossroads. You can't get what you're hoping for on the box. And the other one I would note is that notionally you should be able to get a better job out of the Granite Rapids. So let's go start with a show of hands. Which one of, OK, we're going to ignore Eclipse. We're going to know that Broadwell is slow. Which one of these machines do you think is going to be the most delivering of its promise? Any NVIDIA fans in the house? No? One. OK, John believes in Grace. What about Crossroads? What about that Sapphire Rapids with HBM2? No? Anyone think Granite Rapids will do the job? OK, there's a couple votes over there. And then I guess everyone else likes the traditional Sapphire Rapids. So let's go take a look. And so what I have here is I just computed, based on those numbers, kind of an idealized speed up of what we'd hope to see baseline to the Sapphire Rapids with DDR. So you expect the Broadwell to be slower, right? That's a circa 2018-ish CPU, right? It should be slower. It should be at a quarter to a third of speed. You'd expect the Granite Rapids to be roughly 3x. You'd want to see your Crossroads-like machine to be 4 to 5, and Grace should be roughly 2, if you believed in memory bandwidth. So now let's go take a look. We're going to start with our strong scaling test. So this is a classic strong scaling curve that I will immediately show you looking somewhat different. MPI ranks on the bottom, time on the top. What you want to see here for strong scaling is the strong diagonal line that's nice, happy, and straight. And if I were to stop at 20 processors and like cover up the right-hand side of the graph, that's exactly what you'd see. Well, OK, that's interesting, right? Like you see these flat bits, right, where you hit your strong scaling limit, and they hit them all at different places. And you might even argue that your Sapphire Rapids with HBM never quite hits it, whereas everybody else does at some point or another. So this is hard to tell, are we getting our ideal speed up? So I'm going to rewrite this plot. I'm going to remove the Sapphire Rapids with DDR, and now I'm going to normalize everything to that. So what do we see? We see our older Broadwell machine is actually faster than you think it should be. By a non-trivial amount. Our Sapphire Rapids with HBM, the next one up there in red, is actually slower than the DDR at low core counts, but eventually kind of cruises up to sort of a 2.5-ish range as everything gets going. Grace looks really good. It's definitely in that like 2-ish range that you expect, and Granite Rapids is a bit more variable, and this might be, you know, my limited observations, but it gets up in the 3+ range. So do we hit our sort of ideal ranges? So I added some random little colors for the range we expect to hit in. Broadwell overshoots. Sapphire Rapids with HBM comes nowhere near what you'd expect. Grace actually does really nicely. In fact, at higher core counts, it overshoots. And then Granite Rapids kind of hits its range sometimes. So what do we see here? First of all, one thing about the older CPU is you need fewer ranks to saturate the memory subsystem. And so any older CPU will look good compared to a newer one relative to peak performance, because I can hit peak performance with 36 ranks on a Broadwell machine. I can't hit performance with 36 ranks on Sapphire Rapids with DDR or HBM. And so that's kind of one of the sort of interesting things that pops out of this, right? So peak performance is a bad measure at low core counts, right? What I'd ideally like is rather than have these bands on a single number, right, a band based on peak performance at this number of ranks doing a thing. The other thing I will note is Granite Rapids has 256 cores, and I'm able to get near where I would hope for peak performance with only 100. If I were to run this out further, maybe it'd look better, but I can't compare it to DDR anymore because it's only got 112. Sapphire Rapids with DDR. So that was kind of interesting. So now let's go look at a second one. Let's see if we can see this on other things. So let's look at finite element assembly. And now this is a different story. Where are my 3s? Where are my 4s? I'm sitting pretty much uniformly 1.25 to 1.5. Well, except for Broadwell, right? That's just slow. what's going on here? And I'm going to break that into two pieces. There's two parts. There's a graph fill, which involves allocating memory, and Victor can laugh at me at this point because we've been having a discussion over memory allocation being slow recently. And then we have a matrix fill, which is more pointer chase and hammer on the memory subsystem to add things. And you see very different behavior, right? If I look at that graph fill where I'm doing memory allocation, adding, it gets faster as we throw more ranks at it relative to the Sapphire Rapids with DDR. That's kind of disappointing. We don't see the advantage of the fancier memory subsystem to the extent we want. The matrix, people start to take off. Although I will add, even on the matrix fill, sometimes you see like Grace or the Sapphire Rapids with HBM running slower than the Sapphire Rapids with DDR, which is a little disappointing. So the lesson here is more memory bandwidth does not magically make malloc faster. Does it make it faster? Yeah, a little bit, but not what you'd expect and not what you'd hope for. We can look at the same thing with our strong scaling. So the thing I will note here is because I was doing things in cubes, I only go up to 64 ranks. This is going to be grossly unfair to Granite Rapids and unfair to Grace for that matter as well. But this is what we see. And this is sparse matrix multiplication. There's a ton of memory allocation being timed here. We can see definitely that there's an effect both on the HBM and on the Granite Rapids where things are getting faster relative to DDR, Sapphire Rapids DDR, but it's not where you'd want it to be. Again, you're sort of rank limited there, so that's part of it. And this is our solve phase for Mulu, which should look more like the SPMV. And it kind of does, right? You definitely see as we start throwing more ranks at these fancier memory systems, both in Grace and Granite Rapids and the Sapphire Rapids with HBM, we're getting more out of it. So where are we? What did we get? Could we deliver the promise? The answer is on CG Solve, well, with the exception of your Crossroads-like machine, yeah, you can get kind of what you had hoped for. On some of the other things you don't, right? As you start hitting the memory system through malloc more often, you're not getting quite that level of performance. And so that certainly, even on a CPU where malloc is fast, right, you need to think more about memory allocation than you might have otherwise had to have done, say, 15 years ago. All right, let's go look at GPUs. We're going to play the same game here. So here's a bunch of machines we're looking at. My baseline machine is going to be Vortex. It's a mini Sierra. That's V100s. It's notionally a little under a terabyte a second of memory bandwidth. We have Aurora with the Intel Max, 3.2 terabytes a second. You have Hops, which is our CTS2 machine with H100s, 3.3, 3.4 terabytes a second. I'll skip Eldorado for a moment. You got Frontier, 3.2. So notionally, if I believe what's on the box, Aurora, Hops, and Frontier, so your Intel Max, your H100, and your MI250X, all should be about the same. We'll see in a second. We also add Grace Hopper. So that's 4 terabytes a second. So you expect to see that a little ahead of the pack. And then finally, your mini LCAP, your MI300A, at 5.3 terabytes a second. All right, we'll do show of hands again. Who thinks LCAP is going to win the day? MI300A. Got one vote. All right, we got a couple votes here. Awesome. All right, do we have any NVIDIA fans in the house who would go with Grace Hopper or the H100? Oh, I see a lot more hands. All right. Folks from Oregon, you do not have to raise your hands for Aurora, but you can if you want to. Do anyone think Aurora is going to work well? All right, well, let's go take a look. So we're going to look at a subset of those tests here. But again, right, here is our sort of speed-ups via Vortex, right? We want to see 5, like almost 6-ish from our MI300A, 4.5-ish from Grace Hopper, and we want to see about 3.5 from everything else. Well, what do we get? We're going to start with CG Solve. All right, so this looks a little different because I've only got most of these machines only have 4 GPUs or tiles per, and so we're only going to look at that. Grace Hopper, I only had 1 of them, so you won't see a Grace Hopper on the right side. So we're going to ignore that. So this is speed up versus the V100. And so V100 is normalized to 1. And so what do we see here on a single MPI rank for our CG Solve? We see our H100 sitting at about 3.5. Awesome. That's what we expected to see. Our MI300A is about 2.5. You're like, well, huh. Your MI250 is like 1.25. And your poor Aurora is sitting at about half the speed of the older V100s. When I go to 4 ranks, everything looks really good, and this is partially because Vortex actually gets slower. So I'm normalizing relative to something that's doing something really weird, right? It should be faster. It should be strong scaling, 4 times faster. It's actually slower on that machine. And so everybody else looking good is, I mean, yes, you're faster than the old V100, but not in a way that really sings your own praises. So we'll skip that for a moment, and we'll go to the MPI setup. Remember, this is sparse matrix-matrix multiplication. There is going to be a lot of memory allocation and maybe some hosted device transfer. We're going to look at the same thing. Here, I don't have Aurora results on 4 ranks because the code crashes. Because the sparse matrix-matrix is problematic. What are we seeing here on the 1 rank, at least, where we have everybody in there? There is our V100. Your H100 is about 50% faster. Remember, memory allocation, right? We're not going to see this factor of 3, 4, 5, 6 because CUDA malloc just didn't get that much faster. The results from Frontier are disappointing, but not as bad as results from Grace Hopper. That actually surprised me. I would not have thought that there'd be something going on there. Again, right, that's not a full production system, so there's a chance that there's just something not configured right there. And even the results on the MI300 and the Intel Max from Aurora are also very disappointing. At 4 ranks, things look better. You're looking at roughly 2x on the H100, and your MI300A is now actually a little faster. Frontier is still a little sad. For all the Oak Ridge people, I apologize. These results are real. But there's something as to how Frontier is configured relative to other MI250 systems we can look at that artificially depresses the performance we see on Frontier. So we don't know what, but if that's something you want to talk about, feel free to catch me afterwards. We're going to look at one last thing. We're going to look at our solve phase, right? This is where we can actually see happy results again because there's no memory allocation. So again, there's your V100. You're looking sitting at a 2.5 or a little bit more for your H100 and Grace Hopper. Your MI300A is like 50% faster. The Max actually manages to sneak out a little speed, so yay Intel on 1 rank, and we're just not talking about Frontier. It's not as pronounced on 4 ranks, but you can see stuff as well along those lines. So what can we say about all this? What did we get? Do we get our ideal speedups? The answer is maybe not quite. The closest you're going to see, barring that really wonky bit on Grace Hopper, is the Grace Hopper numbers look pretty good. The H100 numbers look pretty good. MI300A is certainly generally better than the older machine, but not by as much as you'd hope. And to be honest, I think this is consistent with even the LinPack results you saw out of El Capitan, right? You're not getting as close to peak as you would hope to see on a #1 scale computer. And that means there's a lot of headroom there for AMD to work with Livermore to kind of push that through. So it'll be very interesting to see LCAP-like hardware now versus LCAP-like hardware 2 years from now as they've worked on that a bit more and matured the software stack. Clearly, there's something wrong with how Frontier is configured or how our tests are configured on Frontier, so that's something we want to look into. And Aurora is Aurora. What can I say? So sort of to wrap stuff up, one of the cool things about doing performance testing, right, and a bunch of the results I showed you are from our nightly performance tests. I did new special machines like Grace Hopper, NVIDIA Grace, Granite Rapids for this talk, but everything else came out of results we already had. And so by doing performance benchmarking, you can start talking about comparisons across machines in a useful way. So does memory bandwidth matter? On a CPU, yeah, it does, right? And I think that came out with a couple caveats. It's not 1-to-1. And peak bandwidth is not the best predictor at low core counts, right? We saw the overperformance of Broadwell at low core counts because it can saturate its memory subsystem and nothing else can at 36 ranks. Granite Rapids actually does a pretty good job of using its memory bandwidth at relatively low core counts, especially relative to the Crossroads style Sapphire Rapids with HBM architecture, which if I'm running onesies, twosies sorts of jobs of small analysis jobs and lots of them, I'll probably get more bang for the buck out of that than I would out of like a Crossroads machine. And Grace actually looks quite good. I'd certainly seen NVIDIA advertise about how Grace is the best thing since sliced bread. I was a little skeptical, but it actually came out looking all right, which is fantastic, fantastic news. On the GPUs, memory bandwidth matters, but the but here is bigger, right? Malloc really eclipses this in a way that's far worse than you see on a CPU. And you really can't talk about memory bandwidth and performance across vendors. Within a vendor, you can definitely see the improvement, like say from Frontier to Aurora, or on the NVIDIA side from sort of Vortex to, if I had Perlmutter results, you would see a boost there with the A100 to hops. But across vendors, memory bandwidth is not something you can use to really tell you how you should expect performance. So you need to take that into account. And that being said, the vendors are delivering substantial performance jumps as they're improving their hardware and software stacks. And so that's actually really good news for us. See, Kurt, I actually put up the new logo on this slide rather than the screenshot on the old one. Thank you to our friends at the Linux Foundation for having us do that. And again, right, if you want to see more about Trilinos, we'll certainly have time to look at that tomorrow as part of our Trilinos user group meeting. Oh yeah, acknowledgements, hi. Thank you for everyone who let us use their computers. And I'll be happy to take any questions.
Thank you, Chris. A+ on hitting the mark for what I wanted in this session. So, any questions, right? We have like a couple minutes. Oh no, Luke, you can. Yeah. Okay, let's go over there. Wait.
So I noticed you slamming on Malloc a lot. My question is, like GPU run, like the implementation of Malloc and libc and then the GPU runtimes is not necessarily ideal for the kinds of things you're doing. Have you tried using like a suballocator or some layer on top to try and like buffer this?
So effectively, this is a conversation I was having last week with Victor and Roger Pulaski. What we've wound up doing historically is basically caching, memory caching, rather than trying to implement our own memory pool. If writing a memory pool was easy, the vendors would have already done it. Evidently, Todd has an opinion on this. And by and large, they haven't, right? And this is the reason why we have issues with Malloc. So it's certainly, we need to be much more careful with our memory allocation and avoid the small stuff or try to front load it. And so that's certainly something we're looking at. As for like a full-blown suballocator, I mean, that's another bag of worms, and I'd really rather someone else open that, preferably the vendors, but failing that, someone who's not me. All right. We got a mic in the back. Mike, literally Mike.
Yeah, right, two of them. So all things considered, this big transition from CPUs to GPUs, the effort that went into it, and the cost of devices, because we compete with this AI space. What's your ballpark sense of the relative, cost performance? Can you say anything? And I know there's many parts to this, but do you have any response to that going, right now and going forward?
In terms of like, GPU versus CPU, or just the advancement of HPCs?
Okay, performance per dollar, right?
Yeah.
There's lots of ways to answer. Any answer that comes to mind.
All right, so I'm going to knock on Los Alamos briefly. My apologies to my colleagues there. Right, the reason the folks at Los Alamos bought Crossroads is they didn't want to modernize all of their old codes to GPUs. And so they waited while the rest of us were all slogging with our GPU computing and getting our, factor of 3 to 5 speed up in most cases. I think one of the things that they couldn't have done that had the rest of us not done what we did, because I think the push towards GPU forced the CPU vendors to really up their game in terms of, again, right, using my example here, memory bandwidth, right, faster engagement in new memory technology and be able to push things harder and faster. And so I think you couldn't have had Crossroads, or even some of the newer CPUs I showed you here, without basically the GPU to light the proverbial fire under Intel's posterior. I would have loved to have some AMD CPU results to have. I didn't get a chance to run some new epics, but that's on the list of things I want to look at. So I think you can still get decent performance out of a CPU. You're not going to get GPU level performance. As for cost, all of the things I showed you today are incredibly expensive. If you go to Intel's website and you say, how much does a Granite Rapids cost me? And you look at it and you're like, holy cow, that's a lot more than I pay for my desktop computer. And the GPUs are just fantastically expensive. So I don't think, you can't get performance for cheap on leadership class like hardware. It's just not possible.
Okay.
So that's my rambling. Does that work, Mike?
Yeah. One last thing on that, right? If you actually look at list prices, right? We have not gotten a boost in performance per dollar since 2017 or 18, right? We're getting more performance for more money, but that's all we're doing, right? Basically.